Going to continue on with Unit 6, and in this video we're going to talk about learning target 7C, which is what is a logarithmic function. So by the end of this lesson we will be able to convert back and forth from log form to exponential form. We will also be able to evaluate logs without a calculator, as well as expand and condense logarithmic expressions using the properties of logs. So let's start out with what a logarithmic function is. A logarithm base b of a positive number x satisfies the following definition. If I have a base b that's bigger than 0 but not equal to 1, then we say that log base b of x equals y is the same thing as b to the y equals x. So what's going on here is that we get a logarithmic function by taking the inverse of an exponential function. So here in our log function, we can see that our input is the x and our output that we're getting is the y. And in the exponential version here, our input is the y and our output is the x, because we are flip-flopping that input and that output when we get an inverse. Now down below, I've generalized this some more. So we still have log base b, but instead of our input just being x, I want us to think about this more broadly. So I'm going to use a smiley face to represent our input. We would then get an output of star if we're in log form. In exponential form, this would be the same thing as b to the star equals smiley face. Now we're going to use this definition of logarithms to convert back and forth between logarithmic and exponential form. This will actually be our key to solving both logarithmic equations as well as exponential equations in this entire unit, as well as in future math courses from here. Now in this video, what we're going to focus on is just converting back and forth between log form that we have here on the left side, and then to exponential form, which we have here on the right side. So we're going to get practice starting in one form and going to the other, and vice versa. We are then going to talk about the properties of logs and see those in action and see a couple examples, because those will also be tools that we will use when solving logarithmic and exponential equations. So let's start looking at our first sets of examples here. So below we have 5 examples. Each one of these examples is in exponential form, and our goal is to convert the following exponential equations to logarithmic equations. So let's notice some of these. On some of them we'll have the power on the right side, others have the power on the left side. They're both the same thing. We want to pay attention to first what is the base of our exponent, because that base of our exponent will always be the base of our log. And that's the first thing we want to identify here. So in example 1, we have 49 equals 7 squared, which we know is true. If I take 7 times 7, I do get 49. But we want to convert this into log form instead. What's the base in this first equation? So in example 1, our base is 7. So to convert to log form then, we would have log base 7 of our input and our output are going to flip. So since our input here was the exponent of 2, that becomes our output now in our log equation, and our old output of 49 becomes our input for our log equation here. So 49 equals 7 squared in exponential form is equivalent to log base 7 of 49 equals 2 in logarithmic form. So we are not solving anything here, we're just converting back and forth between exponential to log form. Let's look at example 2. So in example 2, we have 5 to the third power equals 125. What is our base in example 2? Our base in example 2 is going to be 5, so we're going to end up with log base 5, since the base of our exponent is the same thing as the base of our log. What will our new input be for example 2? Our new input will be 125, which will leave us equal to our new output of 3. So taking advantage here of inverse functions, which we learned in our last unit, is where we flip-flop the input and the output, or the domain and range, or the x and the y values. So look at example 3. We have 1 over 81 equals 3 to the negative 4th power. What's our base in that exponential equation? So our base in this exponential equation is base 3. So in log form, we're going to end up with log base 3 of, what's our new input going to be? Our new input is going to be 1 over 81, and that will be equal to our new output of negative 4. We have 2 more examples here. Why don't you guys pause the video and solve example 4 on your own first, and then we'll check it together. So for example 4, we have 12 to the 0 power equals 1. In this case, our base is 12, so we're going to get log base 12. Our new input will be 1, and that will be equal to our new output of 0. And in our last equation here, in example 5, we have 9 over 25 equals 3/5 all to the 2nd power. Why don't you guys pause the video here and solve example 5 on your own. So for example 5, our base is 3/5, so that will become the base of our log. So we'll have log base 3 over 5, or base 3/5, of our new input will be 9 over 25, and that will all equal 2. So in these first 5 examples here, we just practice going back and forth between exponential form to logarithmic form. Well, what if we switch and go the opposite way now? So down below in examples 6 through 10, we're going to start with a logarithmic expression, or a logarithmic equation, and convert this to an exponential equation. As a reference, why don't we go ahead and rewrite our conversion here using our smiley faces. So we get log base b of smiley face equals that star is the same thing, or equivalent to, b to the star equals smiley face. So let's look at example 6. We have log base 4 of 16 equals 2. What's our base in example 6? So our base here in example 6 is equal to 4, which means that 4 is going to be the base of our exponential equation. From here, we need to figure out what our input to our exponential equation is. Since log and exponentials are inverses, then whatever our output was of our log will become our input for our exponential. So here in our log expression or equation, since 2 is our output, 2 is going to be our input, so we'll get 4 to the 2nd in our exponential would be equal to 16. The nice thing about converting from a log expression to an exponential equation is that we can always check it. We know that 4 to the 2nd is the same thing as 4 times 4, which would equal 16. So there's a nice way to check these. It wouldn't make sense to have 4 to the 16th power equals 2, because 4 to the 16th power is definitely much larger than 2. So we have a nice way to check these. Let's look at problem 7. We have 6 equals log base 2 of 64. So technically the logs flipped over to the right side of the equal sign this time, but it doesn't matter. I can still identify what my base, my input, and my output are. So why don't you guys pause the video here and decide what our base is for this log equation. So our base in this problem is 2, so we're going to end up with 2 to some power. What will our new exponent be? Our exponent here is going to be 6, and our output will be 64, which we can always check because 2 to the 6th power is equal to 64. Okay, let's look at example 8. We have log base 9 of 27 equals 3/2. What's the base for that log equation? So our base here is base 9, so we're going to end up with 9 to some exponent equals our new output. What will our exponent be in this equation? So our exponent is going to be the 3/2 power, and that's going to be equal to 27. Now we saw exponents like this last semester. Remember, the 3 is technically the power, and the 2 is representing the index. So as a little side note here, 9 to the 3/2 would be the same thing as 9 to the 1/2, all to the 3rd, and then remember 1 over a number is the same thing as that, nth root. So in this case, since we have 1 over 2 as our power, we have a square root. So we end up with the square root of 9, and then that whole thing is cubed. Square root of 9 is equal to 3, and 3 cubed does give us back to 27. So lots of ways to help check our answers as we convert from a log to an exponential equation. Let's look at example 9. We have negative 5 over 3 equals log base 8 of 1 over 32. Why don't you guys pause the video here and solve example 9 on your own first, and then we'll check it together. So first thing we want to identify is our base. Our base is going to be 8. Our new exponent will be to the negative 5/3, and that's going to equal 1 over 32 then. And the negative 5/3 could be simplified very similar to example 8 over here if you wanted to double check this. And then the negative sign is actually going to flip that. So remember, if we have a negative exponent, that's the same thing as 1 over that number to the positive exponent. So it makes sense here that we end up getting 1 over some value, and 8 to the 5/3 will simplify down to be 32. Let's look at example 10. So in example 10 here, we have log of 1 over 100 equals negative 2. Well, in this case, there's no number here written as our base. And if there's no base written, we actually assume that this is going to be base 10. So anytime we see no base written with the log of log, we assume then that our base is going to be equal to 10. Now later on in this unit, we are going to talk about a different type of log called a natural log, where we use Euler's number as our base, so that would be log base e. And instead, in that case, we don't actually write log, we're going to write something else to represent the natural log. There will also be no subscript on that, so I do want to emphasize the fact that anytime we see log written as log, we do assume that it's base 10. In that other case, which we will end up talking about the very end of this unit, we will see what happens with that base. Let's look at example 10. Knowing that information, that our base here is 10, why don't you guys pause the video and write out what the equivalent exponential equation would be. So we have our base of 10. Our exponent is going to be to the negative second. Since that was our old output, that becomes our new input. And that's going to be equal to 1 over 100. And again, we can check this. 10 to the negative second would be equal to 1 over 10 to the positive 2, and then 10 times 10 would give us 100. So far we've done lots of practice going from log to exponential and exponential to log, and we haven't solved anything yet. Well, we're going to change that up and actually put these conversions into play and help us solve some of these problems. So for the following 4 examples, we're going to evaluate the logarithmic expression, and we're going to show all of our work and simplify our answers completely. Now, I know that these can be typed into a calculator, but our understanding needs to come from how the calculator is getting that answer. So we're asked to find the value of log base 2 of 32. Well, let's start off with this expression and turn it into an equation. So I have log base 2 of 32, and I'm trying to figure out, well, what does this equal? I'm going to call it x for now, and I'm trying to figure out what the value of x would be by hand. Well, in this log equation that we have here, if we convert it to an exponential equation, we would actually be able to solve this. So let's take this equation and go to exponential form. So exponential form would have our base of 2, since that's our base of our log. X would be our exponent, and this would be equal to 32. Now from here, that doesn't look all that much better. I now have my x, what I'm trying to find, in an exponent, but I want us to notice some things. What about 32 would allow me to rewrite 32 as 2 to some power? So what power could I use to rewrite 32 as 2 to a number? Well, 32 is equal to 2 to the 5th, so I can actually rewrite the 32 to be 2 to the 5th power. From here, because I have the same base on both sides, that tells me then, and I have nothing else added or subtracted to them, so because I just have 2 to the x equals 2 to the 5th, the same base tells me that the exponents have to be equal, because there would be no other value that my exponent over here would equal my exponent over here if I have the same base. So in the end then, since I have 2 to the x equals 2 to the 5th, that tells me that x has to be equal to 5. Now, sometimes the answer comes that direct with just x equaling the other exponent, and other times we are going to have to do a little bit more arithmetic after we set the 2 exponents equal. This only works though because I have the same base on each side. If I was not able to rewrite 32 as 2 to some power, then I would have to have another way to solve these. And throughout this unit, we're going to see different log equations that we'll be solving, and we're starting off with this kind of more basic type where we deal with the same base and we're actually able to rewrite both sides of the exponential equation with the same base. let's look at problem 12. We're asked to find the log base 9 of 27. So again, I need to create some equation. So I'm going to rewrite our original expression. So we have log base 9 of 27, and we're trying to figure out what this is equal to. So I'm going to say it's going to be equal to x, and our goal will be to solve for this x. First thing we want to do is to convert to exponential form. Why don't you guys pause the video right here and rewrite this from a log equation to an exponential equation. So in our exponential equation, our base is coming from our log, so we'll have base 9 to the x equals 27. Now from here, my goal would be to rewrite the same base on both sides. Now 27 is never going to be able to be 9 to some power. If I try, I could try 9 to the second, but that's already getting me to 81, which is larger than 27. So instead of just rewriting the 27, I'm also going to have to rewrite the 9. Any idea on how I could rewrite 9 to be something to a power? So we could rewrite 9 as 3 to the second power. We would still have the exponent of x. And we could also rewrite 27 to be 3 to what power? So 27 would be equal to 3 to the third. So although 9 and 27 can't be rewritten as each other's base, we can actually rewrite both sides of that equation to be 3 to some number. And we're going to notice that for most of these problems, our goal will be to get a base that's a prime number. So 2, 3, sometimes 5, maybe 7. And then anything past that, we'd have to think about, well, how can we kind of remanipulate this and get strategic with the problem. But for most of these, we will be working with prime numbers as our base. From here, now that we've rewritten with the same base on each side, I'm going to go ahead and multiply and simplify the left side. So 3 to the second to the x, since I have exponent to exponent, those get multiplied to give us 3 to the 2x. That's still equal to 3 to the third. Now from here, since I have the same base of 3 on each side, that tells me that my exponents are equal. So I get 2x equals 3. And we can go ahead and solve for x and get x equals 3/2. And that would be our final answer. Let's look at example 13. So we have log base 4 of 1 over 8, and we're trying to figure out what that's equal to. So if we set this up, I'm going to say that it's equal to x, so that we have some variable that we're working with. Why don't you guys pause the video here and rewrite this in exponential form, and we'll check that together. So exponential form here would have 4 as our base, since 4 is the base of our log, and we'll get 4 to the x equals 1 over 8. Now our goal from here is to get the same base on both sides. Well, we've got a new kind of problem in our way. I have a fraction on one side. So we are going to have to worry about how to rewrite that fraction using properties of exponents. But for now, let's just think about how could I get 4 and the number 8 itself to have the same base. What could I use as my base? We think in example 13. So for both 4 and 8, I could actually rewrite those as 2 to some power. So for 4, we can rewrite that as 2 to the second power. Then we still have the x equals, for the 8, we can rewrite that as 2 to the third. Notice that I still do have 1 over this, since I had 1 over 8 to begin with in my last step. From here, I want to rewrite this so that I just have 2 to a power on each side. Now on the left side, since I have exponent to exponent, those can get multiplied, and we get 2 to the 2x equals, well on the right hand side, we learned with properties of exponents that if I have something in the denominator, I can move that to the numerator, but the exponent becomes negative. So 1 over 2 to the third would be equal to 2 to the negative third. Now that we have the same base on each side, we can go ahead and set the exponents equal. So we'll get 2x equals negative 3, and from here we can divide through and solve for x. So x equals negative 3/2. So we're seeing a new level getting added into each one of these problems. In example 11 here, we were able to get the same base by only having to change one side. In example 12, we had to get the same base by changing both 9 and 27. And then in example 13, we had to again change both the 4 and the 8, but we also had this added step here of rewriting the fraction as no fraction anymore, as our denominator being 1, by moving the denominator up to the numerator, which in turn makes the exponent negative. So this step is coming from a little review, where if I had a to a negative exponent, that would be equal to 1 over a to the n. We're just working backwards and starting with the 1 over, in this case, 2 to the third, so that would be equal to 2 to the negative third. Let's look at example 14. So here we have log base 125 equals 25. Why don't you guys pause the video here and solve this one out on your own first. So I'm going to rewrite our original problem, and this is going to be equal to x. Why don't you guys solve for what x is going to equal? So our first step here, we have to convert to exponential form. So we're going to end up with our base of 125 to the x power equals 25 then. Our goal here is to get the same base on both sides, so we can then set the exponents equal and solve for x. Well, 125 cannot be written as 25 to some power, but I can rewrite 125 and 25 as 5 to a power. Well, 125 would be 5 to the third, and then I still have the x, would be equal to 25 would be rewritten as 5 to the second. Multiplying our exponents on the left-hand side, we get 5 to the 3 times x equals 5 squared. Now that we have the same base on both sides, we can go ahead and set the exponents equal to each other. So 3x is going to equal 2, and we'll get x equals 2/3 as our final answer. And in each one of these, we were solving for x, so that would be what the original log expression would be equal to, since we set this log expression equal to x. So our log of 100 base 125 of 25 would then equal 2/3. We could always check any of these by working backwards and taking our final equation and then rewriting it into exponential form and making sure that it is indeed equal. Now the next portion of this video, what we're going to talk about is something called the properties of logs. So as we start to solve different log equations, we might have more than one log in a problem. In each of our prior 4 examples, we just had one log of some base of a single number. Well, we could actually add, subtract, and multiply, we'll add and subtract logs, as well as multiply by some coefficients or some scalars. So let's talk about the properties of logs. So for any positive number, m, n, and b, where b does not equal 1, we have the following properties of logs. Now, if you're using the guided notes, these are already printed out for you, but if you're using notes in your own notebook, make sure that you are writing down these properties of logs. Our first property of log is called the product property, and that's what happens when I have the log of 2 numbers multiplied inside. So on the left-hand side here, this is the condensed side. I have one single log, that's log base b, of the product of m times n. We can expand that out into 2 separate logs where we add together those logs. So we get log base b of m plus log base b of n. We also have a quotient property where if I have log base b of 2 numbers divided, so log base b of m over n, we could expand this out to be log base b of m minus log base b of n. And our last property of log is called the power property, where we have log base b of m to an exponent now, so hence the name power, since that's our power in our input. We can actually move that in front of our log to be a coefficient where we get n times that log base b of m. It is possible to combine more than one of these together, and we're going to see different examples where we use maybe 1, maybe 2, or maybe all 3. One thing I want to point out is the left side of all of these is what we call the condensed version, because it's simplified down as much as we could, and the right side is the expanded version of each one of these. Now there are times where we start with a condensed version and we want to expand it out, and there are also times where we start with an expanded version and we want to condense it down into a single log depending on the problem. What we're going to do in the rest of this video is practice going from the condensed version to the expanded version, and the expanded version to the condensed version. So we're not going to solve for anything, we're just going to either simplify and condense these down or expand them out, just to get practice using these tools of properties of logs, so that when we get to solving more log equations, we're already able to do this step. So let's look at our first couple examples. So for all of these on problems 15 through 18, we are going to condense and simplify the following log expressions. So we're going to start with something on the right-hand side here that is expanded out and condense it down into a single log, hopefully. One thing I do want to point out is I am required to have the same base. So if I want to add two logs together, I do need the same base. And if I want to subtract two logs down into one log, I need to have the same base as well. So in the instructions, it does say simplify as much as possible. If I have different bases, there's nothing I can do there to simplify this down. So let's look at example 15. We have log base 7 of x plus log base 7 of y. Now I want to condense this down into one log expression, but I have to have the same base. Do I have the same base in example 15? So yes, we do have the same base. We have a base 7 for the first one and a base 7 for the second one. To condense these down together, since we're adding the two separate logs, we're going to be using the product property, and that will allow us to combine these to one single log expression. So we'll get log base 7, and our new expression, our new input here for the log will be x times y. The reason we're multiplying x and y is because x and y were each the individual inputs to the two logs on their own. And when we condense that down together, we get log base b of those two inputs. So the m times the n, or in this case, the x times the y. Now that I'm down to one single log expression and I have no coefficients in front, that's actually my final answer. So in our first example here, I only applied one of the properties of logs. And as we progress through these, we might be applying more than one at a time. Let's look at example 16. We have log base 4 of a plus log base 4 of b minus log base 4 of c. What's the first thing that we need to be true? Well, we need all the bases to be the same. Are all the bases the same? So in this case, yes, all the bases are the same. We have base 4 for each one. And I'm going to take these two at a time. So let's look at how we can combine the first two together. How do you think we can combine those first two terms? So we can apply the product property in our first step here. Since we're adding these two logs together, we can combine that to be log base 4 of a times b. Now we still have minus this log base 4 of c. In our next step, is there a way to combine down the log base 4 of a times b minus the log base 4 of c? There is. We're going to use the quotient property. The reason it's the quotient property this time instead of the product property is because we are subtracting these two log expressions. So what that in turn does is it creates a fraction inside of our log, where the first thing that's actually the positive log is going to be in the numerator. So we'll get a times b over whatever we're subtracting off will be in our denominator. So we'll get log base 4 of a times b all over c. And that will be our final answer for 16. Let's look at example 17. So here we have 3 times log base 2 of y plus 5 times log base 2 of z minus 8 times log base 2 of x. So the first thing I have to look for is to make sure my bases are the same. Are the bases the same? So yes, the bases are all base 2, so this will work to condense them down into a single log. One thing I noticed though is I've got coefficients in front of each one of these logs, which is not something that we've seen before. When I look at the product and the quotient property, it does require here that I have a 1 as my coefficient. So in order to apply the product and the quotient property, I can't have any extra numbers besides 1 in front. So the first thing I actually have to do in this case is apply our power property. And what that tells me is that anytime I have a coefficient in front, that's going to become the exponent inside my log. So applying the power property for each one of these is going to give us log base 2 of y to the third plus log base 2 of z to the 5th minus log base 2 of x to the 8th now. So each one of those exponents moved up, or each one of those coefficients moved up and became our exponent. Now on the negative 8, there's actually two ways to do this. We could bring the negative sign with it, and then this would be a plus sign in front, or I can leave the negative sign down and just take the 8. In the end, we'll actually end up with the same answer. It just changes a couple of our in-between steps. Now from here, we have something that looks very similar to problem 16. I have log of something plus log of something else minus log of something else. So we're going to have to apply both the product and the quotient properties. Why don't you guys pause the video here and finish example 17 on your own. So our next step in example 17 will be to add together these first two logs using the product property, which will tell us that we get log base 2 of y cubed times z to the 5th minus this log base 2 of x to the 8th. Now from here, I want to apply the quotient property to combine the last logs together, which will give us log base 2 of y cubed times z to the 5th all over x to the 8th. And again, the x to the 8th is going to be in the denominator since that's the log term that's being subtracted. Now that we've condensed it down to one log and we have no coefficients in front, that will be our final answer. We have one more example here, in example 18. I want you guys to try example 18 on your own, and we'll actually check this at the start of class tomorrow. Okay, let's look at some examples where we expand out the log expression instead. So here in example 19, we actually have one single log, so we have log base 5 of x times y all over z. Our goal is going to be to expand this out. We're basically going to reverse what we did up above. So the first step I want to take care of is this fraction bar. Well, we can expand this out into be log base 5 of x times y minus log base 5 of z, and that's using our quotient property. And the fact that the z is being divided out means I can rewrite that as a separate log that's subtracted off. The next thing we need to do to expand it out is break apart the x times y, and that would use the product property. So we could rewrite this as log base 5 of x plus log base 5 of y minus, we still have our last log base 5 of z. From here, we're actually done because every single log has only one number, one variable as our input, and we have no exponents in any of those logs. Let's look at example 20. So here we have log base 7 of a to the 4th times b all over c to the 11th. What do you guys think our first property will be that we'll apply here to expand this out? So our first property will be, again, to apply the quotient property since we have that fraction, and we can expand this out to be log base 7 of a to the 4th times b minus log base 7 of c to the 11th, and we're subtracting it off since that's the piece that was divided. From here, what do you think we could do next? So we actually have a couple options. We for sure need to break apart the a to the 4th times the b, and we're also going to have to worry about these exponents. Well, I could take and move the 11 already off of the c, but before I move the 4, I do need to break this apart and be log base 7 of a to the 4th plus log base 7 of b. And then we still have our last log on there, and that's using that product rule. Now our last step from here is going to be to deal with the exponents. So on both the a to the 4th and c to the 11th, we can move those exponents in front using the power rule, and that will become 4 times log base 7 of a plus, on the b, our exponent is a 1, so I can move the 1 down, but that will still leave me with plus 1 log base 7 of b minus, I'll move the 11 down, and we'll get 11 times log base 7 of c then. So in this last example here, we ended up using all three properties of logs to expand this all the way out. One thing I do want to point out is when we're expanding logs, whatever our base is to start, that will be the base of every single log as we expand out from there. So in example 19, we started with log base 5, so every single one of our final answers, or every log in our final answer had a base of 5. Same thing with 20, as we expanded this out in example 20, our base was 7, so all of our logs have a base 7 that we end up with. Now there is one more example with expanding logs in number 21 down here, and I'm also going to leave this to you guys to try on your own tonight. Expand that out, and then we'll check that together at the start of class. So in this video, we learned about what a log is, that a log function is the inverse to an exponential, and that we can convert back and forth between exponential and log form using the definition and taking advantage of the fact that they're inverse functions. And we're going to talk a lot about exponentials and logs being inverses in this unit and apply all those concepts that we learned about inverse functions in our last unit. Now the second part of this video talked about the properties of logs, which is a tool for expanding and condensing logs, which right now might seem a little silly because we don't have anything that we're solving for, but this tool of using the product, the power, and the quotient property for logs is going to help us as we start to solve both exponential and log equations as we continue on. Don't forget to try examples 18 and 21 on your own, and we'll check those at the start of class tomorrow.